Alright, this is section 3.3 from our trig book. We're learning about the sum and different identities for cosine, and here's what they are. I'm sure you could find a proof somewhere if you wanted to. Otherwise, just trust me or the book, and there they are. This is the sum identity because it's plus, but notice how the identity itself has a minus in it, so don't forget that. And then the difference identity is a minus, but the identity that it's equal to has a plus. So kind of the opposite of what we might expect. Okay, first, before we actually learn to use these, let's practice adding and subtracting radian measures. Let's think about some of the radian measures we use a lot. So we have 0, which doesn't even really count as radians because it's 0 whether it's degrees or radians. Then we have like pi sixths and pi fourths and pi thirds, and sometimes we use pi halves, and then of course we have variations of those with numbers on the top, right? So if I wanted to be able to add or subtract radians, because I'm doing sums and differences today, I have to have common denominators, right? Let's see, Jarrett, pick a number, pick one of the radians. Just choose one randomly. Okay, pi fourths. Antonio, should we add or subtract? Okay, we're going to subtract. Christian, pick another random one from the list. Okay, don't do the same one. Pi thirds, that's fine. Okay, can we just subtract these right now without any problem? And if you can, like, get the same denominator in your head really fast and do it, that's fine, but I'm not that good. So let's go ahead and get a common denominator first. So what will the common denominator be? 12ths. So what do we multiply this one by to get 12ths on the bottom? 3. So 3 pi 12ths minus 4 pi 12ths. Okay. That gives us what? Negative 1 pi 12ths. Let's think about these in degrees really fast and see if that sounds correct. Pi fourths is 45 degrees. Pi thirds is 60 degrees. 45 minus 60 would be a negative 15. Does it make sense that 15 degrees would be half of pi 6 since pi 6 is 30? So pi 12ths would be 15, right? Okay. So on part of the problems on your assignment today, you're going to have to figure out ways to add or subtract some of these to get numbers that you want that are in 12ths instead. So my suggestion is to think about these. You'll have them written in your notes, so that'll help. So instead of pi 6, think of it as 2 pi 12ths. Instead of pi fourths, think of it as 3 pi 12ths. Instead of pi thirds, it would be 4 pi 12ths. And instead of pi halves, it would be 6 pi 12ths. That way, when your book asks you to figure out how to add or subtract any of those to find something else, like say it asked you to do 7 pi 12ths, what would you use? 7 pi 12ths would be what? Three pi 12ths plus 4 pi 12ths, which is really just pi fourths plus pi thirds, right? Or what if you needed to find, is there a combination to do 5 pi 12ths? Oh yeah, add 2 and 3. Sorry, I'm not thinking clearly. What about, well, how about a positive pi 12th? You could do 3 pi 12ths minus 2 pi 12ths, or 4 pi 12ths minus 3 pi 12ths, right? But then ultimately you need to remember that these are actually equal to these so that you can know what the numbers are from the chart that we've learned. So, yeah, anyway, does that make sense? You'll see how you'll kind of use it later. Alright, let's do an example of how we might use these identities. These particular identities would be used when you're trying to find the value of something that's not on the chart, but you want the exact value and not just from your calculator. So find the exact, these are examples, find the exact value of cosine 75 degrees. So 75 degrees, is that one of the angles that we have on our charts that we have memorized? No, the angles on our chart are 30, 45, 60, 90, etc., right? 75 is not one of those. So if we want an exact value, we can't use that chart right now as is because it's not on the chart. We can't use a calculator because that won't be exact. So is there some way we can use one of the identities we just learned and do the 75 as a combination of two other angles that are on our chart? See what I'm saying? What angles on the chart would make 75? Okay, but you're using radians, and that's awesome. I'm glad you're practicing radians. If the problem's given to you in degrees, though, it's fine to just do it in degrees. They're going to give you both types of problems. So 75 degrees could just be done by using what two numbers in degrees? Yeah, we could just do 30 and 45, or you could do them in the order 45, 30. That wouldn't matter. Is there another way to get 75 using a different set of numbers on our chart? Like, what if we did 120 minus 45? Would that work? Yeah, we could do 120 minus 45 and use the other identity, use the difference instead of the sum. Of course, that one would be harder to use because it's quadrant 2 angle instead of quadrant 1 angle, but you will have problems today that you'll have to use other quadrant angles. So that's why I just bring it up, because there's more than one way to do each problem. This is definitely the easiest way to do it. Okay, so using the identity we just learned, where 30 is representing alpha and 45 is representing beta, we plug those values into our formula, into our identity. So cosine 30, cosine 45, and then remember the sum identity actually has a minus, sine 30, sine 45. All right. So this means you're finding the ratio for that, for that, for that, and for that. For some reason, I've found in the past that students, sometimes when they're doing these, they forget that once they've done the cosine of 30, they get an answer. The cosine is no longer written down anymore, because the cosine of 30 is a fraction, and the cosine part is gone. The sines and cosines are gone, right? That might seem weird to say. I'm just speaking to mistakes that I see. So from your memorized charts, what is the cosine of 30? Very good. And these next to each other just mean multiply. So we're going to multiply these fractions together. What's the cosine of 45? Square root of 2 over 2. And then sine of 30. And then sine of 45. Square root of 2 over 2. Okay, now order of operations says we multiply before we subtract. So we're going to multiply these two fractions together, multiply these two fractions together, and then subtract them. When you multiply fractions, you just multiply the numerators, multiply the denominators. So square root of 3 times square root of 2 is square root of 6, 2 times 2 is 4, and then 1 times the square root of 2 is square root of 2, and 2 times 2 is 4, giving us a complete total answer of square root of 6 minus square root of 2 over 4. Sometimes the book writes it a different way than that, like they might actually leave the square root of 2 factored out and put parentheses. I don't know why they do. This seems most simple to me. Alright, so there's one example.